Hi everyone. So we will continue with some of the things that we have been doing since last week. We spoke a bit about stacks and queues in one of the previous videos. We spoke about linked lists at some point of time. So we will now continue with something about linked lists. All right. So this lecture is about basic insertion and deletion operations on a linked list. Okay. So before we go to that, let me quickly recap what we have already done about linked lists, which is how do you represent linked lists using array, right? So here it is. So a simple array itself is a linked list in a very trivial way, and you can represent it in several ways. You can think of it as a singly linked list, forward directed, backward directed, or doubly linked list, where you have both next and previous pointers. Then a binary tree as a linked list, right? And again, this can be doubly linked or singly linked. Singly linked, again, two versions. Either every vertex points to its children or every vertex points to its parent. That is what we have seen, right? So in another talk, we will also do a bit about some more examples of linked lists. But before I go to that, let me now consider some basic operations on linked lists. Okay, insertion, deletion, and searching operation. That's what we would like to do. Okay. So what is our assumption here? So if you go back and note here, for instance, if you look at the binary tree uh, as a doubly linked list, there are three pointers here. Key values are the values inside the vertices. So those are always there. There are three pointers here. One is a left child, the right child, and a parent, right? So, and similarly, in a singly linked version, you either have just left and right child, no parent, or you either have just a parent or no child, things like that. And you have this for the array as well. Now note that when you think of stacks and queues as being implemented using arrays, arrays are implemented using linked lists. Therefore, stacks and queues can be implemented using linked lists. Okay, that's an important note. We'll discuss more about that in the tutorial. Nevertheless, the important thing is we are actually dealing with a more general form of linked list. Linked list by itself is very, very, very general. Okay, it's as general as saying a graph or a metric space or a group, something like that. But we are working with linked lists of a specific structure, okay, where basic operations make no sense. So, what is the basic structure that we are interested in? So, we only consider linked lists of a specific form. What is that form? Given a linked list L, all right, and implemented using arrays as seen before, what do we know? Every vertex or node, so to speak, you understand what is a vertex or a node when I say this, has at most one, let us say, up pointer and a fixed number of down pointers. Okay, what do I mean by that? So let me go once again back here. So this is the thing. For instance, as a doubly linked list binary tree, there is an up pointer parent. There is only one, right? But then the children pointers are two, left and right. Okay. As a singly linked list pointing to children, there is no up pointer. That's what I mean. Parent, there is no parent pointer. There are only two down pointers, left and right side. As a singly linked list pointing to parents, there is only one up pointer parent, but there are no down pointers. Okay, so this is the thing. At most one up pointer could be empty, okay, which means, or could be absent, let's say, and a fixed number of down pointers again could be absent. The thing is, you cannot have many up pointers and many down pointers. Okay, that is the only thing I mean here. The set of pointers can be partitioned in two parts where you call one set as up, one set as down. The up pointer set could be empty or have a single pointer. The down pointer set could be empty or have many. Okay, and what is the relationship between up pointers and down pointers? Not much. Okay, in this generality, there isn't much. Okay, this is very, very general. That's the point to know. Okay, when you think of it as a binary tree or as a stack or as an array, there are relationships that you can see. One arrow goes to the right, one arrow goes to the left. But in this generality, you cannot really say much. Okay, but this is a general idea. So here is the thing. Implemented as an array, the way we have seen before, how do we insert and delete elements? Okay, that is the idea. So we will just see two instances of doing that. So, all right. So let us assume for the rest of this discussion that we have a linked list L with parameters. What do I mean by parameters? The key and up and down pointers. Okay, parameters key, up, and then you have down one, down two, and so on up to say down k. Okay, there are k many down pointers and there is one up pointer. Some of these could be absent. It's possible that there is no up pointer. It's possible that there are no down pointers. That is okay. Okay, in that case, the whatever we discuss will only become easier. Okay, it becomes only easier. All right. So this is what it is. And now the thing is, how do you insert an element? Okay. So the first thing, insert. Now, when you insert, what do you want? You are basically inserting a new vertex. Okay, and you want to say where it's going to link to. Right, where it is going to link to. Is that okay? So insert a value, let's say a key, say value A. Where do you want to do it now? Well, you will have to specify some vertex, right? You have to specify the connections between these vertices. Okay, so one of the ways of doing this is to say that search for the key. Assume that all key values are distinct. So let's also assume that all key values are distinct. Is that okay? So yeah, let's just go here. For instance, in this case, all key values are distinct. You see that the basic indices are sort of obvious. Okay, so now insert a value A, say at index I, or rather, not at index I, along up pointer of vertex I. What does that mean? There is a vertex with index I, right? The key value and all those things, parameters and all that we have to see. But the thing is, when you have a vertex I, it has an up pointer, right? So it's an edge going upwards. And you want to insert the value A immediately at the end of that edge. Immediately at the end of that edge. Okay. so that whatever the earlier up pointer was, now the up pointer should point to a vertex with value A, to point to this value A. So let me write A also. All right. So how do we do this? So we do this again via the algorithm. So insert, and what are the parameters now? L. What key do you want to work with? Up, I, A. Okay. Insert L. Let's say I insert into the list L associated to vertex I along the up pointer. And what value do you want to insert? The value A. Okay. So this is my first algorithm. So start, stop. We have seen before. Start and stop are the usual ways of, it's just a nice way of writing the algorithm. Every algorithm begins with a start and ends with a stop. Okay, that's just a basic rule that we have. We have seen this in stats and quiz as well. Okay, so start and stop. Okay, so what do we do now? Now, note that as an array, L has a length. You see, each of these are arrays. So there is a fixed length. You see, so when you want to insert a new element, you need a new object. Okay, a new object. Is that okay? So that is what you will do. So now what you will assign is the following. The length of the list is, let's say, L dot length, and now this element will have index L dot length plus 1. Because L dot length, many elements are already present. Is that okay? So now how do you write this down? L dot L, which vertex do you want to say? L dot length plus 1. Okay, so now we are assuming that if we just say plus 1, then a new space or a new box is created with index L dot length plus 1. Okay, that's usually you're claiming memory and all those things, so we will not go into memory operations. We will just assume that we can claim as much space as we want, as we wish. Okay. So L at L dot length plus 1, this is a new vertex. What should be the value? The value should be key is equal to A. Okay. Next, L dot length plus 1. Now, if this is along the up pointer, okay, looking back, the new vertex will have some down pointer pointing to vertex I. Okay, so let's also add that here with down, let's say R pointing to, okay, down R pointing to up. So up and down R. These are the parameters. Okay. Therefore, the down R pointer must point to the vertex I. So down L of L dot n plus 1 down R equal to I. What next? We wanted this to be integrated, right? The up pointer of vertex I should now point to this new vertex rather than the original thing, right? But you are not supposed to cut it right away. You are supposed to make sure that the original connections are also there. So you first say L dot length plus 1, which is the new vertex, This one's up pointer. What should this point to? The new vertex up pointer should point to whichever vertex was pointed up by vertex I. Okay, so Li dot up. Li was point the vertex L of I, vertex I, which is L of I in the list. Its up pointer was pointing somewhere. The new vertex should point there, and L of I should point to the new vertex. Right? That's what we're doing. So we will first reassign the up pointer of L of I. Is that okay? And now we will reassign the, now we'll change this. So L of I, its up pointer. Now we can change this. This should now point to the new vertex. The new vertex index is L dot length plus 1. Is that okay? So once again, let me repeat. So what are we doing here? We are trying to insert a value A along the up pointer of vertex I. There is a vertex I. Its up pointer should point to a new vertex with key value A, and the new vertex down pointer should point back to I. The new vertex down pointer, the rth down pointer, should point back to I. Okay. So these are our parameters: the list L, the vertex I, up pointer, down R pointer, and the value A. Okay. First thing, what do we do? The moment you say L of L dot length plus 1, it means the array representation that we have seen here, it claims a new memory space with index L dot length plus 1. So new memory space is created for each of the arrays involved. Okay, so now we have a new vertex immediately. Once we have a new vertex, we have to fill all its parameters. Is that correct? We have to fill all its parameters. Okay, so which is the first parameter? Obviously, the key value should be A. That's what we are inserting. Now this new vertex, its down R pointer should point back to the vertex I. So L of L dot length plus 1 dot down R will be I. Now this new vertex, what is it doing? The up pointer of I is being reassigned, right? Because you are including this inside the linked list. So the new vertex up pointer becomes the up pointer of the original ith vertex. So we will give the up pointer of L dot length plus 1 the value that was given to the up pointer of the vertex I. Okay, so at this stage, at the end of this step, both the new vertex and the ith vertex are both pointing to the same thing that the ith vertex is pointing to. Okay, but now the new vertex is pointing to the same thing. The up pointer has been assigned, and now the ith pointer, the ith vertex is not supposed to point to that thing. It's supposed to point to the new vertex. Okay, so that's what we do. So then Li up is reassigned to L dot length plus 1, the new pointer. Is it okay? Are we done? We are not done actually. The moment we create new vertices, we have to fill values for all parameters. What parameters are remaining? Well, these are the parameters that we have: key, up, down 1 to down k, and so on, right? Key is fixed, up is fixed, down R is fixed, but the remaining down parameters we have not assigned, and we don't have anything to assign. So we'll assign it to be the empty value. Okay, so that is the last part. So for, let us say, j equal to 1 to k, okay, this is like a for loop. It will run from j equal to 1, j equal to 2, j equal to 3, j equal to 4, up to j equal to k. Which values do we have to change? All those values which are not down R. Down j, j not equal to 1. So if j not equal to, this is a notation for not equal to, okay? If j not equal to R, what do we have to do? The down j pointer is assigned empty. Remember, this is the notation for the empty value for the pointer, empty pointer. Okay, for every j that's not equal to, sorry, every j that's not equal to R, down j pointer, but of which one? L dot length plus 1 dot j equal to empty. Is that it? Down R pointer has already been assigned. These were the only values that were remaining. So that's it. End if. Okay. And then end for. The for loop ends. Alright. So this completes the insertion into this linked list. Okay. This completes the insertion into this linked list. Now we will do deletion. Okay. So again, delete. But now what vertex do you want to delete? That's a question, right? So now we will assume that so I made a small mistake. Okay, that's where we are. Right. So now we will simply say that in order to delete, we will just mention the vertex. Okay, for now. We will just mention the vertex which we have to delete. That's all. Okay. Just mention the vertex which we have to delete. Okay. So delete vertex I from the linked list. Okay. That's what we do. So now this is much easier because the parameters are just L and the vertex value I. That's all. Okay. So again, start and stop. And the whole algorithm is between start and stop. What are we doing here? Once again, deleting does not mean you're erasing values. Deleting just means you're reassigning the pointers so that this value can no longer be pointed to. Correct? That's how we delete values. Okay. So what are we supposed to do? This vertex, everything that points, every vertex whose up pointer points to this vertex, you forget that and point it to this vertex up pointed. That's all. Is that okay? So this is the idea. So for, let's say j equal to 1 to L dot length. Okay, now I'm saying this little bit quickly, but go back and spend little bit of time on it and you will be able to understand what is going on. Okay, and we'll also discuss this if something is not clear. So for j between 1 to L dot length, we are only concerned with those, first of all, which are not equal to I. But then more specifically, whose up pointed, the vertices which are pointing to I. So if Lj dot up is equal to I, okay, we are comparing, right? That's why we have equal to I. What do? We reassign this to the up pointer of L of I. So that's like saying L of I is now disappearing from the linked list. L of I was pointing somewhere. These LJs, some of them were pointing to L of I. Now you just say LJs are going to point to whatever L of I was pointing to. So L of I vanishes. Okay. So Lj dot up is reassigned to Li dot up. Each of these, for each of the J's for which Lj up is equal to I, each of the vertices J which pointed to I, I'll now say no longer point this way. Wherever I was pointing, point it there. All right. So that is it. Are we done? Well, the up pointers have been done. Now the down pointer. So L of I, so this ends into, that's all, and for. Then the down pointers have to be set to empty because we don't want those down pointers there. Okay. So once again, for say j equal to 1 to, how many pointers are there? K. So that's what we do. Okay. J equal to 1 to K. Li dot down j equal to empty. So it was pointing downwards to certain things. Now we are deleting all those edges by reassigning those pointers to be empty. Okay, and for. Okay, so this completely removes all the edges from the vertex I in that linked list. The up vertex, the up edges, down edges, everything. And therefore that vertex is now as good as having disappeared from the linked list. In other words, we have deleted that vertex from the linked list. All right. Right. That is what it is. So once again, very simple. Okay. The third thing that I wanted to do is once again, now it's a search operation. Search for value A in linked list. Okay. So you are basically searching for key values. And if you get that, what are you supposed to do? You're supposed to give me all the details of that particular vertex where you found this value. Okay. There could be multiple vertices where this is there, but we are assuming that the key values are distinct. Just for simplicity, even if they are not distinct, not a problem. Okay. So give me all the details of the vertices where the value A is present as a key. And if it's not present, say that it is not present. That is what we are supposed to do. Okay. So once again, the algorithm is now called search. Parameters are the list L. In L, you are looking for the value A. Right. So how do you start? Again, start, stop. Now this is the thing. You have to go across all the vertices, right? So for j equal to 1, 2, L dot length. What are you really searching for? You are searching for the key value, right? So if Lj, the j vertex dot key is equal to A. If it is equal to A, then you are supposed to give me all the details, right? You are supposed to give me all the details. So what are you are supposed to return all these values. So let's say return, or rather print, because there could be multiple. Return in the sense when you return the program ends. You don't want it to end. I want you to just give me all these values. Okay. So return print. What all do you want? First of all, the vertex index j, then lj dot up, and all the other parameters also. So lj dot down 1, right? And we assume that k is constant, so we know up to where it goes. So l dot 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 lj dot down. Okay, you print this. You can print the key value also where you already know what the key value is. Okay, so anyways, let's print the key value also. Okay, so lj dot key, which is going to be equal to A anyways, because that's what we are searching for. Okay. Printed. What else? Nothing more. That's what you had to do. Okay. So end if. For every vertex, you do this. You search the key value is A, you print out the details of that vertex, then you go to the next vertex, again check. Okay. End for. Is that okay? Now there's a small catch here. Let's do a little bit of modification. This is the basic algorithm. Let's also do a little bit of modification. What happens in this algorithm? If there is a value A, it will give me the vertex details. But if there is nothing, if the value A is not present, right, then the output is blank. And I'm supposed to understand that the value A is not present. So let's do one more thing. Let's also say that if the output is not present, then I'm supposed to get a message saying that the output is not present. Okay, so that's the additional thing that we do. So in order to do that, we need a flag. What's a flag? Flag is like a variable which takes value 0 or 1. Okay, in this case, the flag does the following. If the value A is present somewhere, the flag will be 1. But if the value is not present anywhere, then it will be 0. Okay, so I start with a new variable flag and I assign it the value 0. At the beginning itself, I'm assigning the value 0. So after running through all this, if the value A was never found, then after the for loop, the flag value will still be 0. But if I find it somewhere, then I need to set the value to 1. So if lj.key is equal to A for some value A, then I say flag equal to 1. So, okay, now it's present that it's possible that lj.key is equal to A for many values. So flag will become 1, 1, 1, 1 many times, but that's okay. As long as it's 1, it is fine. So flag equal to 1 says that I have found A at least once. And if flag remains 0 at the end of this, it means it was never found. Okay, so that's the end of it. So if flag is still equal to 0, then you just give a message, right? Print what you print, the value A is not found. Okay, so value A not found. That's it. Value A not found. Is that okay? And then that's all. You see, if the flag value became 1 anywhere, then this if will not run because then the flag value is 1. So this will not run. This will not print. If A is never found anywhere, if A is absent, then the flag value that was set to 0 will stay 0, and then this if thing will run, and then this message will be printed. Okay. So that completes the search algorithm in the linked list along with the required messages. Okay. So this was the basics about another set of basics about linked lists, which is we consider linked lists where we have one key, one up pointer and a certain set of down pointers. Okay, and then we saw how to insert a vertex, how to delete a vertex, and how to search for a certain value in that linked list. Okay, how about runtime? So we have been doing runtime several times. So note that there are constant many operations, but then there is a for loop. Okay, the loop runs in the first case as many as the number of pointers. Okay, in the second case, there is a loop that runs again as many as the number of down pointers. Down pointers. Okay, there is another loop that runs as many as the length, many steps. Okay, here again there is a loop that runs as many as length, many steps. Okay, so now I leave this to you. So exercise. What is the runtime of these? Okay, what is the runtime of which ones? Insert, delete, and search. Okay, so find it out. Just go back to the video on stacks and queues and you'll see how we were trying to figure out what the runtime was in that case. And now in this case, again, you can go through and try to see if you're able to determine the runtime. Okay. If not, anyways, we'll take this up again in the tutorial. So that should not be a problem. But I want you to try. Okay. Find the runtime of these three operations: insert, delete, and search for a linked list of this form. Is that okay? So that is the end of this video. Thanks for joining.